at Rochester Institute of Technology. Played in New York, he also went to Stuyvesant. And his interests, he did his PhD in extremal graph theory and combinatorial games, and he also likes computation, logic, and game theory in game context.
Okay, so thank you for that introduction. As the slide says, this talk is about correlation clustering. So I'll start by saying just what correlation clustering is and why you might want to do that. So as you might be aware, there are a lot of different models for clustering data according to whether things are similar or different. Correlation clustering is one such model. It was introduced by Bansal, Blum, and Chawla in 2002. And here's the basic formulation. We're going to extend this a little bit and look at some variations on it. But in the most basic form, you have a whole bunch of objects, and for some pairs of these objects, you have a judgment of whether they're similar or dissimilar. So you might imagine, for example, you're trying to do document deduplication. You have a whole bunch of files, and you have some algorithm that says, yes, these look like the same document. No, these don't look like the same document. And that's where you get these similar, dissimilar. And we represent this by saying we've got some graph with a bunch of edges that are either labeled with a plus or a minus. And of course, the problem is these judgments don't need to be mutually consistent. It might be that there is no single way to just put all the similar things together, all the dissimilar things apart. You'll have to make some mistakes. And so our goal is to partition the objects into clusters, and we want to minimize the number of plus edges that go between clusters, because those are things that want to be together but they're not, or the minus edges within clusters because they don't want to be together but they are. So if you look at this complete graph down here, this is a bit misleading. The graph isn't necessarily complete. There could be objects for which we just don't know anything about whether they're similar or not. But if you look at this graph down here, they're similar around the outside, dissimilar on the inside. And it turns out that the best way to cluster these is into groups of 2, 2, and 1. And you can see we're still making 3 mistakes here with these purple edges on the outside. But that's the fewest mistakes you can make on this graph.
Is your definition of a mistake, it's going to be an enumeration?
Yeah, so right now all we're saying is just count up all the edges that aren't going the way they want to. Each of those is a mistake, and for now, all mistakes are equally bad. That's not always going to be the case, but. So what are some graphs you might want to cluster? Social networks are maybe the obvious application. That's why this talk is called Community Detection. You maybe have pairwise connections between people. Some of these connections you know are positive, maybe some of them you know are negative. And you would want to know, well, what are the coherent communities here, right? Maybe I link to your blog, but I'm only linking to it to talk about how stupid you are, in which case that would be like a negative edge.
Why do you think my blog is stupid?
And so this would be maybe the canonical example here. On the other hand, you could also look at, say, gene networks, where you look at different genes being activated at the same time, and you would want to find clusters of genes that are sort of doing similar things. I won't pretend to know anything about the biology of this. I'm just told this is a thing you could apply it to. So, and of course, you could also look at, say, mathematical collaboration networks, where you might want to identify subfields based on who's collaborating with whom. And this is, of course, the most famous one. So all of those are just sort of general things where you might want to cluster. Right? There are other clustering algorithms, maybe or clustering models, which in some cases might be more or less appropriate. So what's unique about correlation clustering in particular is that unlike, say, k-means clustering, you don't specify in advance how many clusters there should be. If I tell you there are like 4 groups here, find the 4 groups, that's some information. But in correlation clustering, you don't get told that in advance. Part of the problem is figuring out how many groups should there be. And because of the way that all mistakes count against you, it's not like just making one big group or everyone their own group is obviously the best solution. And because you're not making sort of any assumptions about the structure of the underlying data, this is sometimes used to model agnostic learning in machine learning. You're just coming at this data without assumptions. What's the best way to explain it? And there's a couple of other problems that this is related to in one sense or another, such as cluster editing, graph partitioning, rank aggregation. So of course, as you might expect, if you want to find the actual best clustering, it's NP hard to do that. And so what we look for instead are approximation algorithms. And what that means in this context, right, there's two ways to think about what's your objective, what are you trying to approximate. I guess it's whether you're an optimist or a pessimist, you can say, I want to have the most edges that are happy, I want to maximize the number of edges that are put where they should be, or I want to minimize the number of mistakes that I make. And these are, of course, the same decision problem, but if you're looking to approximate, your notion of approximation ratio depends on whether you look at it from min or max. And I'm going to be looking at it in this talk in terms of minimizing the number of mistakes. So approximation ratio 2 means I make at most twice the least number of mistakes. And so if I can just have any graph to be clustering, then the best ratio we have is big O log n, where n is the number of objects. There's good reason to think that this is sort of going to be a difficult boundary because there's a very natural linear programming formulation of this that has been proven to have integrality gap log n. So any progress here would be good, but probably hard. If you assume that your graph is complete, which isn't making any assumptions about pluses or minuses, just that we have a judgment for every pair, that's an easier case to deal with. The best approximation algorithm, if you're willing to use a randomized algorithm, is due to Ilon, Charikar, and Newman. And we'll be talking about that somewhat later. And in terms of deterministic algorithms, there's a 4 approximation algorithm due to Charikar, Guruswamy, and Virt. And so the first thing we're going to be doing in this talk is talking about how does this algorithm work and how could we extend it to work in somewhat more general situations. I should mention now, if you have any questions, yeah, just sing out. This talk might actually be a bit short. So here's how the Charikar-Guruswamy-Virt algorithm works. The idea is you want to solve an LP relaxation of your problem and then round that linear program. This is also exactly the linear program that has that integrality gap that I mentioned. So if you look at this linear program here, we have a variable x sub b for every edge or every pair of vertices, since your graph is complete. And each of these variables is going to go between 0 and 1. And I think of if xe is 0, then the endpoints are close together. I'm putting them in the same cluster. If xe is 1, I'm putting them in different clusters. And if you look at this objective function, it's exactly saying, well, I look at these positive edges, being in different clusters is bad. I look at the negative edges, being in the same cluster is bad. And this here is like a triangle inequality. That's just saying if u and v are in different clusters, in other words, if xuv is 1, it can't be the case that both u and z are in the same cluster and also zv are in the same cluster. And in particular, the integer solutions to this, because you have this triangle inequality here, integer solutions of this linear program correspond exactly to clustering. So you can just read off your clustering by saying, look at the equivalence relation of having your xuv be 0. But of course, we're looking at the LP relaxation, and so the optimal value of this might be some fractional solution. So we can solve this in polynomial time, but then how do we get a real clustering out of that? And that's what the second step of their algorithm is just to round this solution. And the algorithm is fairly straightforward. As you start with all your vertices in this active set, as long as you have some vertices left, pick any of them and look at all of the nearby vertices that haven't yet been clustered. Everyone who is distance to you, we can think of x as being sort of like a distance because we have the triangle inequality. We look at everyone who's in this ball of radius 1/2, and that's sort of your candidate cluster. Now, it might be that everyone in your candidate cluster is still pretty far away from you. If it happens that the average distance from you to the elements of T is still at least a fourth, then we say, well, no one really wants to be close to U. Just cluster U on its own and kick it out of the active set and keep going. Otherwise, the average distance is fairly small, and so we cluster U with T, kick all those out of the active set, and just keep doing this.
These sad little singles in clusters.
Yeah. And so it turns out that if you do this, the resulting clustering, this only can increase your cost by at most 4 times. At worst, you multiply the cost by 4 when you do this rounding. And so if you started with a good solution to the LP, well, it was at least as good as your optimal clustering. You only blew up its cost by at most 4, so you're within at most 4 times the cost of the real optimal clustering.
There must be a reason for 4 versus, say, 3.
Right, so I'll talk a little more. So I think for this it just happens, right, so you sort of, this choice of a half as the parameter is sort of, you could have picked like a third or a sixth, and we'll talk more about that later when we extend this. But 4 is just sort of, that you do the algebra, 4 falls out as you aren't doing any better than that. Yeah, if you wanted to talk about the details, we could talk more about that later. So this is the algorithm that we're going to extend. We're going to come back to this later. But first I'd like to talk about how might we extend this basic model of correlation clustering. So the natural thing to do is, what if instead of having this binary choice of plus or minus, if you instead could put weights on the edges, right? Maybe some mistakes are a lot worse than other mistakes. You want to be able to model that. So instead of just putting a plus or minus edge, plus or minus label rather on each edge, we're going to give each edge a non-negative weight, WE plus or WE minus. And when we look at our objective function of how bad this clustering is, we're going to say that edge E is going to cost WE plus if you put it between clusters. It'll cost you WE minus if you put it within a cluster. Possibly these are both positive. Like, there's no reason in this model that you couldn't say that. That edge is just going to cost you something no matter what. And it might not seem like it makes sense to do that, but in some contexts you do actually want both of these to be positive, like when you're trying to sort of average together a bunch of clusterings. You might say the positive weight is the proportion of clusterings in which they appear together. The negative weight is the proportion where they don't. And one thing that's worth noting in this formulation is if both of the weights are 0, we're allowing that too, then this edge is effectively just not there as far as the clustering is concerned. It will never cost you anything if they're both 0. And one maybe negative way to think about this is, well, this means you can represent an arbitrary graph this way, even when you're assuming that G is complete. If you have some edges you don't want to deal with, just set their weights to 0. And so if you just allowed totally arbitrary weights here, and you wanted to find some approximation algorithm, it's going to be at least as hard as that unweighted case where you had that log n gap. So it's kind of hopeless to try to, or maybe not hopeless, but difficult to solve this for totally arbitrary weights. On the other hand, it's known that if always the sum of the weights is 1 for each edge, then this 2.5 approximation algorithm of Eilon, Cherikar, and Newman it goes through and does the job for you. And in fact, there's this nice result that if you have a C approximation algorithm for the unweighted problem, you can transform it and get a 2C plus 1 algorithm under the probability constraints. So this is sort of interesting to me because what it suggests is that there is a sort of boundary between totally arbitrary weights, which are hard, and probability constraints, which are easy, and maybe we can find some intermediate set of assumptions where you still get a constant factor approximation algorithm, but you can express sort of more situations. And another extension that we're going to look at is let's say, so in basic correlation clustering, you can just take any partition at all of the object set, and that is a feasible solution. But maybe in some application, we don't want to have big clusters in the solution, even if the data is otherwise telling you to do that. For example, if you're using clustering to model like assigning jobs to computers, well, each computer can only handle so many jobs. And you can't try to put all the jobs on one computer, even if that would be the most efficient thing to do. So we're going to say that there's some parameter k that represents an upper bound on the permissible size of a cluster. And each vertex is going to have some mu sub v, which measures the sensitivity to the size bound at that vertex. And the idea is, so for annoying technical reasons, we're really saying the upper bound is k plus 1. And so if vertex v ends up having its cluster break that bound by some amount y sub v, then you're going to pay mu sub v, y sub v extra for having that cluster too big. Of course, if you just put all of these penalty terms equal to 0, that would be the same as having no size bounds at all. But if we can handle this more general case, we may as well. On the flip side, if your mu sub v was really large, if it were bigger than all the positive weights, then it would always be profitable if you had a cluster that was too big. Just split off singletons. You'll save so much in these penalties that you won't care about what you're paying in the positive edges. So this soft constraint model can kind of model the case where you just have an absolute bound on size. And so it would be interesting to see how can we adapt existing algorithms to deal with those constraints. And it turns out you can sort of deal with both questions at the same time without losing much power from the original model. And when I say deal with both questions, of course I don't mean that you get to completely general weights, but we'll get some more general. So we can get a constant factor algorithm if we make these assumptions on the weights. We'll assume all the positive weights are at most 1. And you can really think that's just normalizing, right? If I had one that was too big, just divide through or whatever. We're going to assume that all of if I look at any edge, the sum of its weights should be at least 1. And we've also got this assumption that always the sum of the mu's is at most 4. Which, note that since WE plus is at most 1, just having mu equal 1 everywhere would give you hard constraints. So this is, you can represent hard constraints in here. And the probability constraints say that always the sum of these weights should be equal to 1. So certainly if you satisfy the probability constraints, you satisfy this. But what I find somewhat interesting about this is we have this upper bound on the positive weights, but no bound at all on the negative weights. So what you can represent in this model is you can represent negative edges being really, really bad. You can't represent, however, that positive errors should be bad in this model because of this assumption here. If you actually let the negative weights go up to infinity, you get, as sort of a limiting case, the cluster deletion problem, where you're essentially saying, I have a graph, I want to delete edges until it's a disjoint union of cliques. How many do I need to delete? And we can also model sort of intermediate problems where, yes, you can make a negative mistake if you really have to, but it'll be expensive. And intuitively, yeah, there's no reason to think that positive and negative errors should be equally bad. Maybe positive errors are just inconvenient, and negative errors are you put together two chemicals that, I don't know, blow up your lab or something. And so we can deal with expensive negative errors, but not expensive positive ones. And this is a question that I'm not just going to rhetorically answer on the next slide. If there's some good intuitive reason, should it be easier to handle negative errors here than positive ones? I really don't know, but maybe there's a good reason for it. Maybe it's just this is the path I happen to take. So we can modify that linear program that we had before. Before we were summing over positive edges and negative edges. Now instead we have this sum where for every edge you just look at its positive weight times how far apart the endpoints are, plus its negative weight plus how close to get times how close together. And we've got also this penalty term for sizes. And now these two constraints are just saying usual triangle inequality. And this just enforces that y sub v really does model how badly you break your cluster. Again, if you think about an integer solution, this sum here for any particular v is just the number of things that you cluster v with. So if you have more than k neighbors, you're going to have to make y sub v positive and suffer in your objective function. So this gives you a new linear program. We're going to use the same trick of solve the linear program and round. And all we're doing here is instead of having a fourth, or instead of having a half, we just have this alpha. When the average is more than alpha over 2, then we output the singleton. And if you just put in alpha equals a half, you get back out the original Charikar-Guruswamy-Wirt algorithm. And you get different approximation ratios based on what your choice of parameter is here. And so you want to pick your parameter in order to get a small approximation ratio. So if you want to know what...
Go back and ask
Sure.
a really silly question. So how do you get the 4 back in there?
So the way you get the 4 out of this, so if you pick alpha equals a half,
Right.
and certain assumptions are met, which I'll talk about on the next slide, then a 4 will fall. Right.
It shouldn't have been obvious then.
Right. I'm being deliberately cagey here about what approximation ratio you get, because that's the approximation ratio you get, and it's a mess.
Oh, I see.
Now we did a 2 over a half of the face.
Before, that's right.
Right.
All right. No, I was just wondering if it was, okay.
Right. You might also, if you're being particularly perceptive about the 1/2, notice that it kind of looks like you'd be dividing by 0 here if you put in alpha equals a half. But in the only cases where you'd want to use a half, this term kind of just drops out entirely. The mu star also would be 0 in that case, and the right way to think about that 0 over 0 is that it's acting like 0. So we would want to pick alpha in order to minimize this. And in general, you can write down some cubic equation that alpha would have to satisfy, but that's just not going to have a nice closed form solution. I mean, you could write down a closed form solution, but it would be like 10 pages long. So, but you can, for certain special parameter values, you can still get a nice approximation. You can actually get a number out of that. If you look at mu star being 0, so we just ignore the size constraints, and tau, which is just the biggest negative weight, to be equal to 1, then what you have are basically the probability constraints. You're saying all the positive weights are at most 1, and the sum of positive and negative is always at most 1. So you've got maybe a little more wiggle room than probability constraints. But an approximation ratio of 4 falls out of this, because you can just get rid of that twice alpha mu. So this, in particular, that term, you can just omit altogether. And it simplifies to 4. And in general, if you just ignore the size constraints altogether, you'll get an approximation ratio of 5 minus 1 over tau here. So I want to note here, you might think that because I'm allowing these weights to be large, that I would be kind of cheating by taking all those extra costs from the big negative edges and just hiding them in the approximation ratio. And what I would say that this is saying is no, there really is a uniform approximation ratio, even if it costs you $1 million to have some negative edges. On the other hand, if you do want to look at size constraints, it would be kind of silly to introduce them and then keep them equal to 0 the whole talk. If you have hard size constraints and tau equal to 1, you'll get ratio 6 out of this. And for totally general tau and hard constraints, this is 6.3-ish. So that's just, these numbers aren't so important as just you can get coherent numbers out of this. And I'm not really going to be bothering to talk about the proof of this. The proof is kind of you slog through some algebra and you get to the end. Instead, I'd like to spend the rest of my time talking about this randomized algorithm that at least the proof there is more interesting. So I am trained as a mathematician. There will be a proof in this talk. There should be a proof and a joke, but I forgot to write any jokes. So,
That was it.
So I mentioned earlier that there's this algorithm of Ivan, Charikar, and Newman, which they called CC pivot. And this is a 3 approximation algorithm. I mentioned earlier a 2.5 algorithm based on LP rounding. But the 3 algorithm is simpler and doesn't need you to round an LP. And it's a fantastically simple algorithm. You read it while I was blathering. So all you do is you just start with, again, just some set of all your vertices are active. As long as you have some, you pick a vertex at uniform random and cluster it with all its positive neighbors that you still have. We're back to the unweighted case here, where you just have pluses and minus labels again, not weights. So you just pick your vertex at random, cluster it with all its positive neighbors that are still available, and just keep going. Just do this until you've used up all your vertices. And this is so fantastically simple, it's amazing that this is a 3 approximation algorithm, or at least expected 3 approximation. So it's randomized, it could give you a terrible solution, but the expected value is within 3 of the optimum. And the way that they prove that is they do an analysis of the algorithm, and they construct a dual solution to a linear program, a different one, which we'll see on the next slide, which gives you a lower bound on the cost of an optimal solution. So if we want to describe that linear program, I'm going to say a bad triangle in a labeled graph should have 2 plus labels and 1 minus. And the idea is if you look at a bad triangle, however you cluster, one of the edges of the bad triangle is going to be unhappy, is going to be done wrong. Because either you put the endpoints of the negative edge together, and then the negative edge is unhappy, or you put them in different clusters, but then you have to break one of the positive edges. So in a bad triangle forces you to make at least one mistake, or another way of thinking about that is after you've made your clustering, the unhappy edges are going to give you a covering of the bad triangles. And if we write T of G for the set of all your bad triangles, this gives you a linear program where you're trying to minimize over non-negative x sub b, subject to, for every bad triangle, there should be at least one unhappy edge. X sub b here just means the edge is unhappy, the edge gets broken. Unlike the earlier LP, I'm not sure that you can actually read off a clustering just from seeing the solution to this. Maybe you can, but it's not quite so important in this case. So because of this observation that the unhappy edges have to cover the bad triangles, the optimal value of this LP is going to be a lower bound on the cost of an optimal clustering. Because again, here you could have some kind of fractional covering, not necessarily an integer covering. And what Ivan, Charikar, and Newman do is, based on based on an analysis of their algorithm, they construct a solution to the dual of this. So if this is a fractional covering of the bad triangles, the dual problem would be to pack in bad triangles. And they prove that the expected cost of the clustering is at most 3 times the cost of that dual solution, which forces the optimal value of your clustering to be high. And so we're going to look at how might you generalize this to deal just with cluster sizes, not with weights or anything. So we're still just going to have plus and minus labels, but we're going to demand that all of our clusters should have size at most k plus 1. And the observation here is, think about how CC pivot works. You're always picking a vertex and clustering it with its neighbors. Maybe it happened that you gave me a graph where already the maximum degree was at most k, or max positive degree. In that case, when I pick someone and cluster it with the positive neighbors, he's getting at most k people clustered with him. So I would get this for free, that all the clusters would have size at most k plus 1. And so what we want to do is, well, first find a set of edges, such a set of positive edges, so that if I pretend they're negative, then that is true. If I pretend that all these edges in x are negative, then the positive degree should be at most k everywhere. After I do that, I'll just run CC pivot and use the clustering that it gives me. It might not be obvious you can do this first step in polynomial time, but for example, if k were 1, you'd just be looking for the complement of a maximum matching, which you can do in polynomial time. And in fact, you can solve this problem using matching techniques. And because of what we were saying about CC pivot, it's clear that whatever clustering this gives you, maybe it's good, maybe it's bad, but it definitely has all the clusters of size at most k plus 1. What's less obvious is that, in fact, this is a 7 approximation algorithm. It seems like once I start pretending that these edges are negative instead of positive, I'll get a clustering, but maybe it was a terrible clustering for the original graph. But in fact, it's within a factor 7 of the best you can do, subject to that constraint.
Subject to the k plus 1 constraint?
Right. So, so in other words, if you were really looking even at the clusterings that broke that constraint, well, you should expect that maybe those could be way better. But
And this is still an expected value.
Right. This is still, the expectation of this is within 7. So, proving approximation ratio 7 is hard. I'm not going to try to do that. Maybe I'll outline a little bit. But if you only wanted approximation ratio 11, I can kind of explain that. So I hope you like linear programming, because there's going to be a lot of it in this proof. So let's look at this modification of the covering problem. Again, this is just the problem that we saw where you want to minimize the sum of your x sub b's subject to you cover all the bad triangles. And now also we're going to require that if I look at any vertex and I sum over all its positive neighbors of how unhappy the edge is, that should be at least d plus minus k. And in other words, right, it's easier to look at this the other way around. Only k of your incident positive edges could hope to be happy, because you're only going to be in a cluster of size k plus 1. And that's what this constraint models. And we're going to try to construct a solution to the dual of this linear program using the dual that you get from Eilon, Charikar, and Newman. So I'm going to make g prime to be a copy of g with all the x edges switched to negative, which indeed satisfies the degree constraint. And we're going to use pi prime, the dual solution that Eilon, Charikar, and Newman give us, to get a dual solution to this. So if you go and you take the dual, I can't take the dual of a linear program in my head. Maybe you can. But this is what the dual looks like. You're trying to maximize, your variables are your bad triangles, and they correspond to bad triangles and vertices. I'm trying to maximize the sum of weights for the bad triangles and this sort of weights for the vertices with these coefficients given by their degrees. And that's subject to this packing constraint that you just get out of the original problem. And also, if I look at the positive edges, not only when I sum up the triangles containing that edge should it be at most 1, but also when I look at the endpoints of that vertex. I guess it's not written down, but UV are the endpoints of E, that these should all add up to at most 1. And you can think of this, yes?
It's unclear to me. How you say I'm using the original formulations duals here? There are different formulations with weights now. I mean, constraints on the size of the cluster.
Right, so the idea is what we're going to do is we're going to go from g to g prime and run CC pivot on g prime, which is this sort of deleted graph. I'll get a dual solution to the problem for g prime, and I want to modify that to get a dual solution for g. I'll talk more about what that means in detail later, so maybe that'll clear up the question a little bit. So, when you've got the dual, when you're looking at your dual problem, for each constraint in the original problem, I'm going to get a variable in the dual. So each bad triangle, the variable corresponding to its constraint will be pi sub t. Yeah. Similarly, for each of these vertices, the variable corresponding to that will be a sigma v. And that's right. And so you sort of say, okay, Yeah, and if you run through and take the dual, this is what you end up getting. That, yeah, I'm not sure that I'm going to try to do the.
I'm sorry, yeah, I got it.
Okay. Yeah,
I got confused, yeah.
the subscript is maybe a little confusing there. So the idea is we go down to this deleted graph G prime, and we get a dual to the original problem there. And in that original problem, you don't have these constraints. You don't have this second row of constraints. And what we'd like to do is say use this pi prime for G prime. It's a packing of the bad triangles in G prime, and just use it here. Just take that exact solution, drop it in.
So it's not actual dual, it's an approximation of a dual obtained from just packing the bad triangles in the original formulation.
When I say the original formulation, I mean,
I know.
yeah, I mean exactly this. This sort of weak, not obviously, yeah. Yeah, the dual of that. Where was I? Right. So we'd like to just take that packing of bad triangles in G prime and use it for a packing of bad triangles in G, and just ignore these sigma variables altogether, and that seems like it should give me exactly like I should just be able to use it. The problem is in pi prime, when I went and deleted those edges, maybe I got some new bad triangles. And those bad triangles have variables in the dual for G prime, but they don't appear here. And so there's no variable corresponding to those bad triangles in this dual. So I can't just do that. I can't use those variables. So okay, how about we just ignore them? If you look at a triangle that's bad in G prime but not G, well, it has exactly one negative edge. That negative edge must have come from X, because otherwise it was bad in G as well. So the triangles that are bad for G prime but not for G must have had all positive edges in G and then contained exactly one X edge. But both of these duals, you pack the triangles, which means if I look at any X edge, the total weight of all the triangles containing that edge should be at most 1. And so when I sum over all of these new bad triangles, their total weight is at most size of X, because they each contain an edge from X. And so if I throw out all those triangles and put all my sigma v's equal to 0, I'll get a feasible solution to this dual problem, and its value will be at least the value of pi prime minus the weight of the triangles I threw away. Okay, that's kind of nice, but I don't know how these quantities compare to each other. This alone won't get me any kind of approximation ratio. So let's forget this for a little bit. We totally ignored the sigma v's. That obviously you're not going to get a solution by doing that. So let's ignore the pi variables instead and see if that helps. It's always best to try to solve a problem by ignoring things, and sometimes that works. So if you ignore the pi variables altogether, what does your problem look like? You're trying to maximize over non-negative sigma v's of this weighted sum, just subject to all your sigma u plus sigma v should be at most 1 for every positive edge. And this is sort of a simpler linear program. This itself is the dual of just wanting to minimize over non-negative x sub b, subject to, for every vertex, the sum of your incident edges should be at most your positive degree minus k. And if you stare at this for a couple minutes, you'll realize, oh, that's exactly the problem of I want to delete as few edges as possible in order to make all the positive degrees at most k, which is what we solved and what we can solve in polynomial time. And so this has a feasible, so if you look at this dual problem, it's got this feasible solution where you just take your sigma v and put it to be a half when d plus is greater than k and 0 otherwise. You could have just put everything equal to a half and it would have been a feasible solution, but we're trying to maximize why would I give positive weight to these things that'll cost me in the objective function. So that's why we put those to be 0. And now if I look at this set X that I formed, think about the most obvious way to delete edges and get your degree down. You could just go from vertex to vertex and say, I go to my first vertex, I just kick out arbitrary edges until I get the degree down to k. I do that over and over again everywhere, just finding it greedily. And I would certainly get size at most. Well, I sum over all the guys with too much degree. How many edges did I have to delete? And you might do better than that, because sometimes you'll get 2 for the price of 1. But certainly you'll use at most this many edges. And this is just twice the value of the sigma I just wrote down. And now if I think about these pi t variables and put them all equal to 0, we can think of this sigma as being a feasible solution to the modified LP. And what we just argued over here is that the value of sigma is at least half the size of x. OK, so that's nice, but maybe x is tiny and it doesn't help me. It seems like all I've done is find 2 solutions that might be bad. Well, how about we put them together? I found a feasible solution using only the triangles. I found a feasible solution using only the vertices. And notice I've got a minus and a plus. So if I just take this linear combination, or...
Sorry, the sigma is actually the sum of all the sigma v's, is that correct?
Yes.
Okay.
Yes, this sigma v is just notation for subscripting into the vector.
Sum of those sigma. Okay.
Right. If we're being really, really technical, it's all the sigma v's and also zeros for all the triangles. So if I take so I've got these 2 feasible solutions to this linear program. And so if I take their convex combination, that's also feasible. And if I put them together in just this ratio, I'll get 3/11 value of pi prime minus 1/11 the size of x. Now let's look at the cost of your clustering in G and G prime. Right, when I went from G to G prime, I ignored these x edges. And maybe those edges were good in the G prime clustering, but they turn out to be bad in the G clustering. So I might have suffered an extra cost of x in my clustering. Ilan, Charikar, and Newman say the cost in G prime is at most 3 times the value of pi prime. And, but now what this tells me is the cost in G, expected cost in G, is at most 3 times the value of, is at most 3 times, it's at most E prime plus the x edges that maybe went from good to bad. But if you just compare that to that, you'll see that's at most 11 times the value of xi. And what this is saying now, in other words, is the expected cost of your clustering is at most 11 times the cost of your dual solution. And that says you have approximation ratio 11. So in some sense, we're using the fact that you're simultaneously trying to solve this problem of getting the degrees down and also getting a good clustering. And it turns out you can kind of solve them both at the same time and get still a finite approximation ratio. So you might ask, how could you actually get, well, you might ask that, or you might just ask, why am I still talking? Yeah, I've got time. So you might ask, OK, how would you get that to approximation ratio 7? And it's tough. There's like a lot of technical details. But basically, so you look at this triangle packing LP over here. And what you might notice is if I, instead of saying just over non-negative x sub b, I wanted x sub b to be 0 or 1, I would get an integer linear program. And the value of this is still a lower bound on the cost of your optimal clustering, because the bad edges that are covering your bad triangles, they are, 0, 1 variables. And you can find that edge set x, the smallest set to delete, in polynomial time. And in general, we think of integer programs as being hopeless. But you notice that x itself solves an integer program, which is to minimize over 0, 1 variables, subject to this positive cost being at least d minus k. And I'm using scare quotes here around dual solution. If you take this integer program and throw in just a whole bunch of cuts, you'll get a bona fide linear program with the same optimal value, right, with the same vertices. And so I can find a solution to the dual of that huge, probably complicated linear program that'll have the same cost, just using a strong duality of linear programming. So the idea is, right, we're adding some cuts to this integer linear program, and we get a real continuous linear program. And we're going to do this same kind of factoring trick that we did before. You can think of what we were doing before is Separately, we dealt with the dual variables for the triangles and also the dual variables for the vertices, and then we put them back together. And so you can do a similar thing over here, but this is an integer program. The idea is that when I look at the cuts that I add to this, which aren't even necessarily all the cuts, since that set x is solving an integer linear program, it turns out that you can just let x worry about those dual variables that correspond to those cuts you added. What do the cuts actually look like? I have no idea. It's probably very complicated. Right? I mean, the matching polytope, we know what it looks like, but for higher things, we don't. And that's essentially the sort of problem you're solving. The point is we don't need an exact description of the cut constraints, because if we're clever about how we add cuts, we can just let x take care of all of it, because the cut constraints for the linear program that correspond to x and the cuts that you add to this are going to be exactly the same, are going to have the same objective functions. And so you can just let x worry about taking care of the integer part. And so you're getting, you're only getting still, that should be a 7, by the way, not a 6 up there. I actually kind of noticed a couple of holes in this argument while I was putting this together, but was able to patch them, but apparently forgot to change. So yeah, in some sense, this is the weaker result, because it's not even guaranteeing you the same approximation ratio you got through the LP rounding, but I think there's something neat going on in the proof, and so that's why I wanted to share it. So I have these acknowledgements. These are the people who gave me money. Some more people who gave me money. I want to thank the organizers, especially for being so great about this last-minute substitution that I had to make. And yeah, I want to thank you all for coming to this talk. That's all I got.
Any questions?
I'm always happy to ask questions.
Sure.
I'll ask you an inane one and a non-inane
Okay.
one. The non-inane one is that you get these bounds on the expectation, right?
Right.
But you're kind of just worried about a polynomial time algorithm, so your polynomial time algorithm goes, and it gives you something.
Right.
But if you knew something about the distribution of what it gave you, even in a simple case, you could run it repeatedly.
Mm-hmm.
You know, if you know a little bit about the distribution, you could say, well, I should run it 3 or 4 times and that will give me a gain. I was wondering, you might dramatically improve the expectation.
Improve the expectation, or?
Yeah, because the expectation would now be the expectation over the maximum.
Oh, I see what you mean. Okay.
The stochastic algorithm. But it would still all be polynomial time.
Yeah, I don't know that there's any specific, like, concentration results about this. Maybe if you went back and really looked very closely line by line at the actual paper, you could pull out a concentration result. But I don't think that in the original paper that Ilo and Charikar Newman did that. It might be worth, doing that. And
So do you mean this distribution on weighting on different nodes, and what distribution?
So the thing is, he runs the algorithm, right? And then he gets a ratio. And the expected ratio is some value, right? If I run the thing, I actually get a value.
mm-hmm.
Now, there's a
Sometimes it's
distribution.
better,
I don't
sometimes
care
it's
about
worse.
this.
Distribution of the result in the previous
Right.
iteration, and then you just rerun.
I just
Yeah,
rerun it,
makes sense.
and like, they're very simple. If I don't fret about where you got the thing from, right? Because you run the algorithm and it gives me a value. There's lots of great results about, well, the maximum of 2 random variables, or the
Right.
maximum of 3, and so that's.
I mean, I guess now that I've thought about it for like 15 more seconds, it seems like I don't think you could really improve your approximation ratio that way. It seems like what you'd really be trying to prove that way is how reliable is this? Like, where's my like 95% or whatever?
You would improve your approximation ratio, because it would be it'd be the expectation of a convex function of your random variables, so necessarily be larger.
Like sometimes it's good and sometimes it's bad. You have an average.
Yeah.
You're picking
Okay.
ones.
Yeah. So.
The smaller or larger, or whatever you prefer
Right.
of the multiple runs, you'll necessarily do better.
Right. So maybe it could be done. That's, I guess, the best thing I can really say about
Okay,
it.
so that was the intelligent question. The unintelligent question is that the kind of fundamental assumption is you have a bivariate comparison. Right?
Mhm.
That every 2 objects you can go, how similar are these, or how
Right.
dissimilar? And then I was wondering, so if I have a triple comparison. So if I do the hypergraph equivalent or something,
Right.
right, does everything suddenly break if I start fretting about, because it's a bit like, the reason I have it in my mind, it's a bit like using covariance when you do, so as you said, k-means clustering, something using covariance rather than something that takes into account comparisons of triples or quads. So I could take a hyper edge and say, that's an unintelligent question.
Right.
You're better off not answering it.
Right. I see what you're going for there. It's it's.
People haven't really considered that in this field.
No, I don't think anyone's really considered trying to go to hypergraphs. I think just because graphs are hard enough already.
Any questions? All right.
Okay. Thank you.
Thank you.